Good day, esteemed researchers and viewers worldwide. Today we delve into the intriguing question, MambaOut. Do we really need Mamba for vision? This groundbreaking research by Weiho Hu and Shenxiao Wang challenges the necessity of the Mamba mechanism in visual recognition tasks. Stay tuned as we explore their innovative MambaOut models and the compelling insights they offer into the future of visual recognition technology. Our research delves into the application of the Mamba mechanism in visual recognition tasks. We found that Mamba, with its inherent suitability for long sequence and autoregressive tasks, may not be necessary for all visual tasks, particularly those that do not exhibit these characteristics. This led us to propose two hypotheses centered around the structured state space models, or SSM, which is the token mixer in Mamba. The first hypothesis suggests that SSM is not required for image classification, as this task doesn't align with either the long sequence or autoregressive characteristic. The second hypothesis, however, posits that SSM could potentially be beneficial for tasks like object detection, instance segmentation, and semantic segmentation, which do exhibit the long sequence characteristic, despite not being autoregressive. Our research led to the development of a series of models we've named MambaOut. These models are constructed by stacking gated CNN blocks, and notably, they exclude the structured state space models, or SSM, which is the core token mixer of Mamba. Now let's talk about how these models performed. In terms of image classification, MambaOut surpassed all visual Mamba models, effectively validating our first hypothesis that SSM is not necessary for this task. However, when it came to detection and segmentation tasks, MambaOut didn't quite measure up to the performance of state-of-the-art visual Mamba models. This outcome supports our second hypothesis, suggesting that SSM may indeed have potential benefits for tasks that align with the long sequence characteristic, even if they are not autoregressive. The crux of our research revolves around the challenges faced by transformer models such as BERT, GPT series, and VIT. These models struggle with long sequences due to the quadratic complexity of their token mixer, attention. This complexity issue has led to the development of various token mixers with linear complexity, and more recently, the emergence of RNN-like models. However, the application of these models in visual recognition tasks has shown mixed results. Now let's take a look at the MambaOut framework, which is the focus of our study. This framework, designed for visual recognition, has a hierarchical architecture with 4 stages. The architecture of the gated CNN block, a key component of this framework, is highlighted here. The crucial distinction between the gated CNN block and the Mamba block is the absence of the SSM, or state space model, in the gated CNN block. This difference forms the basis of our investigation into the necessity and effectiveness of the SSM in visual recognition tasks. Our motivation stems from the need to address the computational challenges posed by the quadratic complexity of the transformer's token mixer, attention. In response, various token mixers with linear complexity have been introduced, including RNN-like models like RWKV and Mamba. However, we face a specific problem. Despite their promising capabilities, these RNN-like models have shown underwhelming performance in visual recognition tasks when compared to state-of-the-art convolutional and attention-based models. This leads us to the importance of our problem. Mamba's token mixer, the structured state space models, or SSM, is ideally suited for tasks with long sequence and autoregressive characteristics. However, not many vision tasks possess both these characteristics. This mismatch could potentially lead to a performance drop, raising the question of whether we really need Mamba for vision tasks. This forms the crux of our investigation. While there have been numerous attempts to incorporate Mamba into visual recognition tasks, resulting in models such as Vision Mamba, V-Mamba, Local Mamba, and Plain Mamba, these models have unfortunately not lived up to expectations. The performance has been less than stellar, leading us to question the necessity of Mamba in these tasks. In response to this, we've proposed two hypotheses. The first suggests that the structured state space models, or SSM, which is the token mixer of Mamba, may not be necessary for image classification tasks. The second hypothesis, however, posits that SSM could potentially be beneficial for tasks like object detection and instance segmentation, as well as semantic segmentation. To validate these hypotheses, we've developed a series of models called MambaOut. These models are designed to test the effectiveness of Mamba and SSM in visual recognition tasks. The results of these experiments will provide valuable insights into the role of Mamba in these tasks. Our research introduces a novel perspective on the use of Mamba blocks in visual recognition tasks. We've identified that the key difference between gated CNN and Mamba blocks is the presence of structured state space models, or SSM. This understanding led us to develop a new model, MambaOut, which uses Mamba blocks but without SSM. This unique approach allows MambaOut to serve as a natural baseline for future research on visual Mamba models. It's a significant step forward, providing a new direction for exploring the potential of Mamba in visual recognition tasks. Our research proposes two hypotheses concerning the role of structured state space models, or SSM, in visual recognition tasks. The first hypothesis suggests that SSM may not be necessary for image classification tasks. This is because these tasks do not exhibit the long sequence or autoregressive characteristics that SSM is ideally suited for. On the other hand, our second hypothesis posits that SSM could potentially be beneficial for tasks such as object detection, instance segmentation, and semantic segmentation. These tasks align with the long sequence characteristic, even though they are not autoregressive. To validate these hypotheses, we developed a series of models called MambaOut. These models are constructed by stacking gated CNN blocks, providing a unique approach to visual recognition tasks. Through this methodology, we aim to shed light on the necessity and potential benefits of SSM in the field of visual recognition. The crux of our research lies in the key distinction between gated CNN and Mamba blocks. The primary difference is the existence of the structured state space models, or SSM. In our proposed models, which we've named MambaOut, we've removed the SSM. To test our hypotheses, we designed experiments using ImageNet for image classification, and COCO and ADE20K for object detection and instance segmentation tasks. We evaluated the performance of these models based on their accuracy. The results were quite revealing. Our MambaOut model surpassed visual Mamba models in image classification, effectively validating our first hypothesis that SSM is not necessary for this task. However, when it came to detection and segmentation tasks, MambaOut fell short, thereby validating our second hypothesis that SSM may be potentially beneficial for tasks that follow the long sequence characteristic. These findings underscore the potential of SSM in certain visual tasks and the importance of aligning model design with task characteristics. Our research offers some key insights into the application of the Mamba mechanism. We found that Mamba is ideally suited for tasks that exhibit long sequence and autoregressive characteristics. However, not all tasks meet these criteria. For instance, ImageNet image classification does not possess these characteristics. Therefore, introducing Mamba into such tasks is unnecessary and may not yield the desired performance improvements. This understanding guides us in identifying the most effective use cases for Mamba, ensuring that we leverage its strengths in the most beneficial manner. Our technical results reveal some intriguing findings about the MambaOut model. In the realm of image classification, we tested MambaOut on the ImageNet dataset. The results were quite promising, with MambaOut surpassing the performance of visual Mamba models. This effectively validates our first hypothesis, suggesting that the structured state space models, or SSM, may not be necessary for image classification tasks. This finding also raises a broader question about the necessity of the Mamba mechanism for all visual tasks. Next, we'll delve into the performance of MambaOut in detection and segmentation tasks. Stay tuned as we unpack these results and their implications. Our experimental results shed light on the performance of the MambaOut model in detection and segmentation tasks. When tested on COCO and ADE20K datasets, MambaOut did not match the performance of state-of-the-art visual Mamba models. This finding supports our second hypothesis, suggesting that the structured state space models, or SSM, could indeed be beneficial for tasks that align with the long sequence characteristic. This underscores the need for further exploration of Mamba's potential in handling tasks with long sequences. Our research critically examines the necessity of the Mamba mechanism in visual tasks. We proposed two hypotheses about the role of the structured state space models, or SSM, in image classification and object detection and segmentation. To validate these hypotheses, we develop models called MambaOut, which do not include SSM. Our findings show that MambaOut surpasses visual Mamba models in image classification, thereby validating our first hypothesis that SSM is not necessary for this task. However, when it comes to detection and segmentation tasks, MambaOut falls short, validating our second hypothesis that SSM may be beneficial for these tasks due to their long sequence characteristic. These conclusions provide valuable insights into the application of Mamba and SSM in visual tasks, and we believe they will guide future research in this area.